The memoryless property concerns the property of random variable. Not all random variables, very limited amount of random variables. So what is the memoryless property? Well, if x is the non-negative random variable, we say it has the memoryless property if, and then this expression, it's a conditional probability, you note, then equals to a unconditional probability, where s and t are bigger than or equal to 0. Interpretation, we want to kind of look at this, we want to interpret this thing before we actually go and prove it, but to be able to interpret it, it would help if we know the following, that the only discrete random variable that has this memoryless property is the geometric. Let's just say discrete random variable is only the geometric distribution that has this. And continuous random variable, non-continuous random variable, only the exponential distribution. The exponential distribution has this property. So there's only like 2 distributions that has this property. Okay, let's talk about what this means in the context of a geometric distribution. Before I do that, let's just say, so I'm going to give you interpretation of this equation in the context of geometric distribution, and then for an exponential distribution, and then we're going to prove it, that geometric distribution has this property and exponential distribution has this memoryless property. Okay, interpretation first, because no point doing the proof if we don't even know what this thing means. Geometric distribution. Recall that the geometric distribution is to do with the number of the number of trials until we get our first success, or it could be defined as the number of failures until we get the first success. Okay. So in that case, let's just say let x be the number of trials until we get the first success. As an example that we all understand, a boring example, nevertheless, it's, let's say that we've got a coin. How many times do we have to throw this thing up in the air until it lands on a head? Then what this says, conditional probability says that if you haven't already got so x is the number of trials until you get a head. If you haven't already got a head within t tosses, the chance that you get a head occurring s tosses after another s tosses is the same as if you started afresh from the start. That's the same as the chance that you've just get a head after s tosses. So to put it another way, you've thrown the dice t number of times and you haven't got a head. So that says this number of trials to get a head exceeds this number of tosses. So you've thrown it t times and you haven't got a head. The chance that you need at least another s throws to get that head is the same as if you just started from the beginning, that you need at least you need more than s throws to get ahead. In that respect, the fact that you've already thrown it t times is neither here nor there in getting ahead in at least another s throws. That's what this is saying. So basically it's forgotten that you've already thrown it t times. If you need at least another s throws to get ahead, it's the same as if you did it from the start. In other words, it's a bit like a goldfish memory. It kind of forgets. Right, similar thing with the exponential, and you'll see the story is very similar. So, okay, the exponential distribution is used to do with like a waiting time until the first event occurs. So let's pick one that you all understand. Let x be the time you've been at college until you get your first date. This says that if you haven't already got a first date within t time period, that you have to wait another s periods beyond t to get your first date. Is the same as waiting for at least s periods from the start of college. In other words, it's forgotten that you've already been at college period t. Waiting at least s periods after t is the same as waiting from s period from the start. And then we can kind of see that both these, so these two distributions are very similar then, aren't they? They're to do with, this is to do with number of trials until the first success. This is to do with the waiting time until the first success. Once that something happens, it's game over. Okay, now I'm going to kind of prove it first for the geometric, and I'll do it two ways. For each of these we can do it in two obvious ways. And the method, you don't have to do both methods, but I'll just talk about the method now, because it's up to you which one to use. Let's see, method 1, we're going to prove these using a cumulative density function. And method 2, we can use the probability mass function for the discrete case and the probability density function. Okay. So which method do we use depends on what we know about. Do we know the CDF of these two guys, or do we know the probability mass or the probability density function of the two guys? And just to say, it's going to be less work using the CDF. But first we have to know what the CDF is, and that might be something that is not provided to you in the exam. It might be that you're given these guys in the formula sheet in the exam. Okay, so let's start off first with geometry. Basically, for each of these two, I'm going to do the same thing. First, let x follow the given distribution, and then note what the CDF is, or PMF or PDF, depending on which method I'm going to use, and then obtain an expression for the left-hand side. And I'm going to do the same by obtaining an expression for the right-hand side, and then say left-hand side equals the right-hand side. Done. In case, just one more thing before I go to the proofs. In case any of you are asking, well, are these two events independent? Say this event A, this event B. You should be clear that these events A and B are not independent, because you know that if A and B are independent, given that B has happened, doesn't affect probability of A, so it would just be equal to probability of A. And this is not what this expression is saying. And here it's quite obvious why A and B are not independent, because they're both kind of to do with time t. Alright, geometric. Let x